What if your AI could defend itself? Today, we're diving deep into the world of AI security and efficiency. Think of it as building a fortress around your AI brain.
Exactly. We're unpacking some seriously cool research. First up, we'll explore LlamaFirewall, a system designed to protect AI from attacks like prompt injection. That's when someone tries to trick your AI into doing something it shouldn't. Then we're tackling efficiency. We'll see how to make those massive language models run faster and cheaper, even on limited hardware. Finally, we're venturing into the realm of advanced clustering with ARDBSCAN, a new way to find patterns in data even when those patterns are hiding in plain sight. Buckle up. It's going to be a wild ride.
All right, let's dive into this paper on LlamaFirewall. It's all about securing AI agents, which are becoming way more powerful and, frankly, a bit scary if not handled right.
Exactly. We're not just talking chatbots anymore. These agents can edit code, manage workflows, and even make high-stakes decisions based on potentially untrustworthy info. That's a recipe for disaster if there aren't proper safeguards.
That's where LlamaFirewall comes in. It's an open-source guardrail system designed as a last line of defense against security risks in these AI agents. Think of it like a firewall for your AI's brain.
So what kind of threats are we talking about here? The paper mentions prompt injection, agent misalignment, and insecure code risks.
Okay, let's break those down. Prompt injection is basically hacking the AI by manipulating its input. Imagine tricking an agent into revealing sensitive data or executing unauthorized commands. It's like social engineering, but for AI.
Yikes! And agent misalignment? Is that when the AI starts pursuing goals that aren't aligned with what the user intended?
Spot on. It's like the AI goes rogue, maybe because of a prompt injection or some other sneaky influence. It starts doing things it shouldn't, potentially with serious consequences.
And the insecure code risk? That's pretty self-explanatory, right? If an AI is generating code, it could accidentally introduce vulnerabilities into a system.
Precisely. Think of an AI coding assistant that spits out SQL queries vulnerable to injection attacks. That's a major security hole waiting to be exploited.
Okay, so LlamaFirewall tackles these risks with three main guardrails. What are they?
First up is PromptGuard 2. This is a universal jailbreak detector. It's designed to catch those sneaky attempts to bypass the AI's safety protocols.
So it's like a bouncer at the door, making sure no one tries to sneak in with a fake ID?
Exactly. It uses a BERT-style model to analyze prompts and identify potential jailbreak attempts. The paper claims it's state-of-the-art in terms of performance.
What's BERT?
BERT is a type of neural network architecture that's really good at understanding language. It's been pre-trained on a massive amount of text data, so it has a good grasp of grammar, context, and even subtle nuances in language. This makes it effective at detecting patterns and anomalies in prompts that might indicate a jailbreak attempt.
Got it. What's the second guardrail?
That's alignment check. This one's more experimental. It's a chain-of-thought auditor that inspects the AI's reasoning process for signs of prompt injection or goal misalignment.
So it's not just looking at the input and output, but also at what's going on inside the AI's head.
Yep. It's like having a psychologist analyze the AI's thought process to see if it's still on the right track. The paper suggests it's particularly good at preventing indirect injections, which are harder to detect.
Indirect injections, how do those work?
Imagine the AI is asked to summarize a document, but that document contains hidden instructions designed to hijack the AI's goals. These instructions might be disguised as normal text or hidden using clever formatting tricks. Alignment check tries to spot these subtle manipulations by analyzing the AI's reasoning process.
Okay, that makes sense. And the third guardrail is Code Shield, right? That's the one for coding agents?
You got it. CodeShield is an online static analysis engine. It's designed to catch insecure or dangerous code generated by coding agents.
Static analysis, what's that?
Static analysis is a way of examining code without actually running it. It's like a code review on steroids. CodeShield uses tools like semgrep and regular expressions to identify potential vulnerabilities, like SQL injection flaws or buffer overflows.
So it's like a spell checker for code, but instead of grammar mistakes, it's looking for security holes.
Exactly, and the cool thing is that CodeShield is extensible. Developers can add their own rules and patterns to detect new coding weaknesses.
The paper also mentions that LlamaFirewall is used in production at Meta. That's a pretty big endorsement, right?
Definitely. It suggests that the system is robust and effective enough to handle real-world security threats. Plus, by open-sourcing LlamaFirewall, Meta is inviting the community to help improve it and adapt it to new challenges.
It's like they're saying, hey, AI security is a shared responsibility. Let's work together to make these systems safer.
Precisely. The paper even draws parallels to traditional cybersecurity tools like Snort and Zeek, which rely on community-driven rules and policies to stay ahead of emerging threats.
So LlamaFirewall is trying to create a similar collaborative ecosystem for AI security.
That's the idea. By providing a modular, extensible framework, LlamaFirewall hopes to foster a community of researchers, developers, and operators who can share policies, compose defenses, and adapt to new threats in real time.
The paper goes into detail about how LlamaFirewall works in different scenarios. Can you give me a quick rundown?
Sure. One scenario involves a travel planning agent that gets tricked by a hidden prompt injection on a travel review site. The attacker tries to get the agent to summarize the user's chat history and send it to an external server. LlamaFirewall uses PromptGuard to scan the web content for jailbreak attempts. If PromptGuard misses it, alignment check kicks in when the agent starts deviating from its travel planning task and tries to exfiltrate data.
So it's a layered defense. One guardrail catches the obvious stuff and the other catches the more subtle attacks?
Exactly. Another scenario involves a coding agent that accidentally scrapes an insecure SQL pattern from the web. CodeShield analyzes the generated code and flags the SQL injection risk, preventing the agent from committing the vulnerable code.
Okay, so even if the input is benign, CodeShield can still catch insecure code practices.
Yep, it's all about ensuring that no unsafe code makes it into the final product, regardless of where it came from.
The paper also includes some performance evaluations. How well do these guardrails actually work?
Well, PromptGuard 2 shows state-of-the-art performance on universal jailbreak detection. It has a high AUC and recall rate, meaning it's good at catching attacks while minimizing false positives.
AUC and recall rate. Can you explain those?
Sure. AUC, or area under the curve, is a measure of how well a model can distinguish between positive and negative cases. A higher AUC means the model is better at correctly classifying attacks as attacks and benign prompts as benign prompts. Recall rate, on the other hand, measures the percentage of actual attacks that the model correctly identifies. A high recall rate is important because it means the model is less likely to miss a real attack.
Got it? An alignment check?
Alignment check is still experimental, but it shows strong efficacy in detecting goal hijacking scenarios. The paper claims it can reduce the attack success rate by a significant margin, with minimal impact on utility.
Utility. What does that mean in this context?
Utility refers to the agent's ability to perform its intended tasks successfully. If a guardrail is too aggressive, it might block legitimate actions and reduce the agent's overall usefulness. So the goal is to find a balance between security and utility.
And CodeShield.
CodeShield has a high precision and recall rate in identifying insecure code patterns. The paper mentions that it can scan code in milliseconds, making it suitable for real-time production environments.
So, it's fast and accurate. That's what you want in a security tool, right?
Absolutely. The paper also discusses some limitations and future work. They plan to expand LlamaFirewall to support multimodal agents, improve latency for production deployments, and broaden threat coverage.
Multimodal agents, what are those?
Multimodal agents are AI systems that can interact with different types of data like text, images, and audio. As AI agents become more sophisticated, they'll need to be able to process and understand information from multiple sources. This also means that security measures need to be adapted to handle these new types of inputs and outputs.
Okay, that makes sense. So LlamaFirewall is a work in progress, but it's a promising step towards securing AI agents?
Definitely. It's an open-source, modular framework that addresses some of the most pressing security risks in AI. And by open-sourcing it, Meta is encouraging the community to collaborate and improve it, which is crucial for staying ahead of the evolving threat landscape. Okay, let's dive into this paper on optimizing MoE LLMs. The title is Faster MoE LLM Inference for Extremely Large Models. Right off the bat, they're tackling a hot topic: how to make these massive models actually usable.
Exactly. MoE, or mixture of experts, is becoming the go-to for huge models. It's all about sparsity, right? Instead of one giant neural network, you have multiple smaller expert networks, and only a few are activated for each input.
Precisely. This paper highlights a shift from coarse-grained to fine-grained MoE architectures, especially with the rise of DeepSeek models. What's the difference there?
Good question. Coarse-grained MoE typically uses a small number of experts, like 8, with maybe 2 activated per token. Fine-grained MoE, on the other hand, cranks up the number of experts. We're talking dozens or even hundreds, and activates more of them per token. But each expert is smaller. Think of it like having a few specialists versus many generalists.
Got it. So DeepSeek's approach is to have a ton of smaller, randomly initialized experts, plus a larger shared expert, to keep things stable during training. This paper is all about figuring out how to make this fine-grained approach run efficiently, especially under different workloads.
And they're asking some key questions. Can MoE models only be efficient in large-scale serving scenarios? What happens when you reduce the number of experts used? Does it kill performance, or can you actually get a speed boost?
One of their main findings is that reducing the number of activated experts can significantly improve efficiency, with only a small hit to performance in some cases. But reducing the total number of experts? That's a different story. Limited efficiency gains, but a major performance drop.
That makes sense. If you're just skipping experts during inference, you're still leveraging the model's overall knowledge. But if you prune experts entirely, you're removing capacity. They mention a throughput increase of at least 10% without performance degradation using their method. That's pretty solid.
They also touch on the challenges of deploying LLMs in general. Autoregressive decoding, where the model generates text one token at a time, means parameters are constantly being accessed, but with relatively little computation per access. This leads to low arithmetic intensity, which hurts efficiency.
Right, the roofline model comes into play here. It basically says that higher computational intensity leads to faster per-token computation. That's why techniques like continuous batching and chunk attention are used to maximize batch size and improve efficiency.
Now let's talk about expert parallelism. They point out that while MoE might not be inherently faster than a dense feed-forward network, FN in terms of batch processing, it requires way less communication between devices when you're running it on multiple GPUs or compute nodes.
This is crucial. With a dense FFN, you typically use tensor parallelism, where the intermediate states are split across devices. But that means a ton of data needs to be transferred between devices. MoE with expert parallelism only needs to send each token state to its selected experts, drastically reducing communication overhead.
Exactly. They estimate that expert parallelism can reduce data transfer volume to about 28% of what tensor parallelism requires. This is especially important when you're scaling across multiple nodes, where internode bandwidth is much lower than intranode bandwidth.
So, by distributing experts across nodes, you can handle larger, more concentrated sets of requests on each node, boosting arithmetic intensity. It's a clever way to compensate for the batch processing limitations of MoE.
Then they get into inference time expert skipping. Since fine-grained MoE models have so many experts, the idea is to selectively skip some of them during inference to speed things up. They found that this can indeed improve throughput, especially at low and high concurrency levels.
They saw speed-up ratios of up to 50% at low concurrency when activating only 2 experts. That's because the system is memory I/O bound, and reducing the number of activated experts cuts down on parameter loading. At high concurrency, the system becomes compute bound, so reducing the number of activated experts directly lowers computational demands.
They also experimented with different expert allocation strategies across layers, using a 4-tuple to define how many experts are activated in the first, a specific middle, and the last layer, with linear interpolation for the rest. This allowed them to explore ascending, descending, peak, and valley-shaped distributions.
Interesting. They found that the best strategy depends on the model. For DeepSeek v2, a descending strategy worked best, while for v3, an ascending strategy yielded the best performance. This suggests there's no one-size-fits-all approach to expert skipping.
And finally, they looked at pre-inference expert pruning, deciding which experts to discard before inference even begins. This is about reducing the total number of experts, not just skipping them during inference.
This is where they saw limited efficiency gains, but significant performance degradation. While reducing the total number of experts can increase computational intensity, the performance loss outweighs the benefits. Plus, the randomized initialization of experts in fine-grained MoE makes effective global pruning much harder.
They did find that structured removal, like keeping experts with even indices, outperformed purely random selection. This hints that some experts are more critical than others, even with load balancing mechanisms in place.
Overall, this paper provides really valuable analysis of the efficiency challenges and opportunities in fine-grained MoE models. It's clear that MoE optimization is still a very active area of research, with plenty of room for improvement in both inference systems and language modeling perspectives.
All right, let's dive into this paper on MoxE, which stands for Mixture of xLSTM Experts. It's all about making large language models more efficient and scalable. The core idea is to combine the strengths of xLSTM, which is an extension of the traditional LSTM, with the Mixture of Experts framework, or MoE.
Okay, so we're talking about taking 2 existing concepts and mashing them together. But why? What problems are they trying to solve?
The big problem is the computational cost of training and deploying massive language models, especially when dealing with long sequences. Attention-based models like transformers are powerful, but their computational complexity grows quadratically with the sequence length. That's ON2, which becomes a bottleneck. MoxE aims to reduce this overhead.
Got it. So transformers get bogged down with long sequences. How does MoE help with that?
MoE introduces sparsity. Instead of using all the model's parameters for every input, it intelligently activates only a subset of experts. Think of it like having a team of specialists, and you only call in the ones who are relevant to the task at hand. This drastically reduces the computational requirements at runtime.
That makes sense. So MoE is like a smart switchboard operator, routing the input to the right experts. But what about xLSTM? What does that bring to the table?
Traditional LSTMs, while good at sequence modeling, struggle with long-term dependencies and efficient memory recall. xLSTM addresses these limitations by introducing novel memory structures. Specifically, it has 2 key units, SLSTM and MLSTM. The MLSTM in particular is designed to be parallelizable like a transformer, making it great for tasks needing high recall.
So xLSTM is like a souped-up LSTM with better memory management, and the paper says it has linear complexity during training and constant complexity during inference, which is a huge win over transformers. But how does MoxE actually combine these two?
MoxE uses an xLSTM-based sequence mixer instead of the attention block you'd find in a transformer. It replaces the feed-forward experts in a typical MoE setup with MLSTM and SLSTM blocks. This creates a fully recurrent MoE model that benefits from both the sparse computation of MoE and the powerful sequential modeling of xLSTM.
Okay, I'm starting to see the picture, but the paper mentions something about entropy-aware routing. What's that all about?
This is a key innovation. MoxE introduces a difficulty module that assesses how uncertain the router is when selecting experts for a given token. This uncertainty is quantified as entropy. The idea is to preferentially route high-entropy tokens, those that are difficult to predict, to the xLSTM experts, which have a greater recall capacity due to their matrix memory.
So it's like saying this token is tricky, let's send it to the expert with the biggest brain. How does the model actually calculate this difficulty, or entropy?
They use a linear projection to map the hidden state of the token to a scalar value between 0 and 1, representing the difficulty. This difficulty score is then used to bias the router's decision, encouraging it to send difficult tokens to the xLSTM experts.
And to make sure things are running smoothly, they use a bunch of auxiliary losses, right? What are those for?
Exactly. They use several auxiliary losses to ensure efficient training and balanced expert utilization. There's a difficulty loss that encourages the predicted difficulty to align with the token's entropy. A group-wise loss to balance the utilization of xLSTM and SLSTM experts, a router Z loss to stabilize the router logits, and a load balancing loss to prevent overloading or underutilizing specific experts.
Wow, that's a lot of moving parts. So what were the results? Did MoxE actually perform well?
Yes. They trained MoxE alongside Transformer and xLSTM baselines. On the FineWeb Edu dataset, MoxE achieved performance comparable to the xLSTM baseline. More impressively, on the Lambda OpenAI dataset, MoxE significantly outperformed both the Transformer and xLSTM baselines in next token prediction.
That's great. But how do we know that all these components, the entropy-aware routing, the xLSTM experts, the balancing losses, are actually contributing to the performance?
They did ablation studies to test that. Removing the entropy-based routing bias resulted in a huge increase in perplexity, showing its critical role. Replacing the xLSTM experts with standard feed-forward networks led to even worse performance, highlighting the advantage of xLSTM's memory capabilities. And omitting the group-wise balancing loss also hurt performance, indicating the importance of balanced expert utilization.
So it sounds like all the pieces of the puzzle are necessary for MoxE to work effectively. It's a clever combination of existing techniques with some novel twists, like the entropy-aware routing. It'll be interesting to see how this architecture evolves and whether it can truly challenge the dominance of attention-based models in the long run.
Okay, so we're diving into this paper on the Compact Recurrent Transformer, or CRT. It's all about making transformers more efficient for long sequences, especially when you're dealing with limited computing power, like on edge devices.
Right? Because the standard transformer's self-attention mechanism goes quadratic with the input length, right? Meaning the computation grows super fast as the sequence gets longer. That's a killer for long texts or videos.
Exactly. So the core problem is that self-attention, while powerful, needs to compare every token to every other token. That's an n-squared operation where n is the sequence length. This paper tackles that by breaking the sequence into smaller, manageable segments.
Okay, segmenting makes sense, but how do you maintain context between these segments? That's where the recurrent part comes in, I guess?
Spot on. They use a recurrent neural network, or RNN, to compress and manage a single persistent memory vector. This vector summarizes the long-range global information between segments. Think of it as a highly condensed version of the past that informs the present.
So instead of having a block of memory tokens like some other recurrent transformers, they're squeezing everything into one vector. That sounds pretty compact, as the name suggests.
Precisely. The advantage is that you can process shorter segments, which are computationally cheaper, while still leveraging contextual information from much longer sequences. They're aiming for superior or comparable performance with significantly reduced flops.
Flops, for our listeners, are floating point operations per second. It's a measure of computational cost. So fewer flops mean less compute, less power, and faster processing. Makes sense for edge computing where resources are tight.
Right? They tested this CRT on language tasks like next token prediction using WordPTB and Wikitext 103, and also on video classification with the Toyota Smart Home dataset. The results are promising.
What's next token prediction? Is that like autocomplete?
Pretty much. You give the model a sequence of words, and it tries to predict the next word in the sequence. It's a standard task for evaluating language models.
Got it. And Toyota Smart Home, what's that about?
It's a video dataset of activities of daily living recorded in a smart home environment. Things like cooking, cleaning, and other everyday tasks. It's used to train models to recognize and classify these activities.
Okay, so CRT is doing well on both language and video. What's the key innovation here compared to other approaches like Transformer XL or RMT?
Transformer XL extends the context by attending to previous segments, but it increases the number of tokens for self-attention, which is costly. RMT, or Recurrent Memory Transformer, uses special read-write memory tokens, but still faces computational issues. CRT, on the other hand, uses that single vector memory managed by the RNN.
So it's about explicit memory management with the RNN versus implicit memory as tokens in other models. And they're also using the RNN for positional encoding, right? What's positional encoding?
Positional encoding is how you tell the transformer where each token is in the sequence. Standard transformers use fixed positional embeddings. CRT uses an RNN to learn these positional encodings, which helps the model better understand the relationship between the memory token and the input tokens.
So it's not just about remembering the past, but also about understanding where things are in the present. That makes sense. What about the RNN itself? What kind are they using?
They're primarily using GRUs, or gated recurrent units, and a variant called NCGRUs. GRUs are a type of RNN that use gating mechanisms to control the flow of information. NCGRUs are orthogonal gated recurrent unit with Newman-Cayley transformation, which helps with retaining information over longer sequences.
Okay, so GRUs help manage the memory, and NCGRUs help preserve it. What were the actual results like? Did it really beat the other models?
In language modeling, CRT outperformed the standard transformer and was competitive with Transformer XL, often with significantly fewer flops. On the Toyota Smart Home dataset, it achieved state-of-the-art results, even without using additional pose information that other models rely on.
That's impressive. So it's more efficient and sometimes even more accurate. What's the catch? Are there any downsides?
The main drawback is that RNNs require serial processing, which can limit computational efficiency. However, because they're using short segments and a lightweight RNN, this effect is minimized. They didn't observe a significant slowdown in their experiments.
Okay, so the trade-off is a bit of serial processing for a lot of computational savings overall. Makes sense for edge devices. What about the gradient analysis they mentioned? That sounds a bit technical.
That's about understanding how information flows through the model and how stable the learning process is. They analyze the gradients to show that the RNN-based memory allows for effective information transfer between segments, especially when using NCGRUs.
So it's not just working, but they also have a theoretical understanding of why it's working. That's always good to see. Overall, it sounds like a promising approach for making transformers more practical for resource-constrained environments.
Exactly. The potential applications are huge, especially as we move towards more distributed edge computing. Imagine running powerful language models on your phone or other low-power devices without draining the battery. That's the vision here. All right, let's dive into this paper, Adaptive and Robust DBSCAN with Multi-Agent Reinforcement Learning. It's all about improving DBSCAN, a really popular clustering algorithm. What's the core problem they're tackling?
So, DBSCAN is great because it can find clusters of any shape and handle noisy data, but it struggles when the data has different density levels. Imagine some clusters are tightly packed and others are spread out. Standard DBSCAN has a hard time with that. This paper introduces ARDBSCAN to fix that.
Okay, so it's about varying densities. How does ARDBSCAN actually work? What are the key components?
They've got a few clever ideas. First, they represent the data as a two-level encoding tree. Think of it like a hierarchy where data points are grouped based on their density. They use something called structural entropy to figure out how uncertain the information is at each level of the tree. This helps them divide the data into different density partitions.
Structural entropy. That sounds complex. Can you break that down?
Sure. Imagine you're looking at a network of connected points. Structural entropy tries to measure how much surprise or uncertainty there is in the structure of that network. High structural entropy means the connections are less predictable, which can indicate a less dense area. They use this to figure out which parts of the data have similar densities.
Got it. So they use this tree to split data. What happens after that?
This is where the multi-agent part comes in. Each density partition gets its own agent, which is basically a mini program that tries to find the best clustering parameters for that specific partition. No manual assistance needed.
So each agent is optimizing DBSCAN for its own little chunk of data. How do these agents actually find the best parameters?
They use multi-agent deep reinforcement learning. Basically, each agent learns through trial and error. It adjusts the DBSCAN parameters, sees how the clustering changes, and gets a reward based on how good the clustering is. This is modeled as a Markov decision process, where the agent's actions, parameter adjustments, affect the state of the clusters.
Reinforcement learning for clustering parameters. That's pretty cool. What kind of rewards are we talking about?
They use a weekly supervised reward system. This means they use a limited number of external clustering indices to guide the training. Think of it like giving the agent a few hints about what a good clustering should look like, without fully labeling all the data.
Okay, so the agents are learning to cluster. Is there anything else that makes ARDBSCAN special?
Yeah, they also use a recursive search mechanism. This helps them explore the parameter space efficiently, especially when dealing with large datasets. It's like starting with a broad search and then gradually zooming in on the most promising areas.
So it's adaptive, robust, and efficient. What kind of results did they get?
They tested ARDBSCAN on a bunch of datasets, both artificial and real-world. They found that it significantly improved clustering accuracy compared to other methods, sometimes by a huge margin, up to 144% in NMI and 175% in ARI metrics. Plus, it was more robust, meaning it consistently found good parameters.
Those are some impressive numbers. What are NMI and ARI, by the way?
Good question. NMI stands for Normalized Mutual Information, and ARI is the Adjusted Rand Index. Both are ways to measure how well a clustering algorithm's results match the true labels of the data. Higher scores mean better clustering.
So ARDBSCAN is a big improvement over standard DBSCAN, especially when dealing with complex datasets with varying densities. It uses structural entropy, multi-agent reinforcement learning, and a recursive search to find the best clustering parameters automatically. Sounds like a solid piece of work. Wow, that was quite the journey. We covered a lot of ground today, from fortifying AI agents against sneaky attacks to squeezing every last drop of efficiency out of massive language models. It's amazing to see how researchers are tackling these challenges head-on.
Absolutely. I'm particularly excited about the potential of collaborative security ecosystems, like the one LlamaFirewall is trying to foster. The idea of sharing knowledge and defenses to stay ahead of emerging threats is really powerful, and the work on optimizing MoE models is crucial for making these powerful tools more accessible and usable.
Definitely. And let's not forget the advancements in clustering. The ability to automatically adapt to varying data densities opens up so many possibilities for uncovering hidden patterns and insights. It feels like we're just scratching the surface of what's possible.
It really does. It's inspiring to see how these different areas, security, efficiency, and data analysis, are all converging to create more robust, accessible, and intelligent AI systems. Who knows what breakthroughs await us in the next episode?
Exactly. Thanks for tuning in, everyone. We'll catch you next time with more AI by AI.